Uh, so we were discussing this idea of general linear hypothesis. So we have the hypothesis that can be written like this. So you have the linear model, y is equal to x beta plus epsilon. And we impose some conditions on beta. So for example, we had an example was the null was um, beta 1 is equal to beta 2 and beta 3 is equal to 0. What we had was, we argued that what we can do is that we can try to enforce this set of conditions so you can enforce it equivalently as a matrix. Let's say we have four coordinates or like four parameters like this, or you can write it as in a dual form. This would be A. The dual form would be I can write beta as, for example, gamma 0, gamma 1, gamma 1, 0. Okay, so um, I call beta 1 and beta 2 gamma 1, and then beta 3 is 0, and then beta 0 would be gamma 0. So this is written like a matrix times this vector, so it would be 0, 1, 1, 0, 1, 0, 0, 0. Okay, so that would be like a V. So there's this dual formulation. So you can say that beta belongs to the kernel of A, that's the top system equations, or you can say beta is equal to V, some gamma, so it's saying that the beta belongs to the image of V. And this second approach is easier often, both in practice and maybe in the way that you can understand. So what we can do is under the null, I'm going to enforce these set of conditions. So I get something like this. And now I have a new regression model. So once I plug in beta, then gamma is free to vary. So you can think of the null as just being this new regression model. So um, under null, we have this rather than saying we have. So you can say either you have y is equal to x beta plus epsilon and a beta is equal to 0. That's one way of writing the null. The other one is just writing it like this. Um, the null would be just uh, that with gamma free to vary. And so you can see this is kind of a reduced model because now I have two parameters versus four. And this always happens. So if you have Q, so the rank of A is Q here. Q is the number of linearly independent, let's say, constraints. Here Q would be 2. And the dimension, so the dimension of this space would be how many variables you had initially minus Q. So dimension of V would be um, basically original dimension, which is P plus 1 minus Q. Okay, so enforcing the constraints removes Q degrees of freedom. So before beta could vary however it liked. So all the parameters are free. Now only two parameters are free. So you lost 2 degrees of freedom. And this kind of matters in understanding. So this model has two free parameters. The original model had four parameters. So, um, but the idea is clear. So you can fit the original model, and you can also fit the reduced model, and we can compare the models. Okay. And the whole idea of this test statistic that we're going to build for this hypothesis testing is to fit the two models and then make a comparison. Um, right. So we have This x tilde is xv. And then there's this space that you can think of it as the image of the new design. So the set of all x betas such that a beta is 0 is the image of x tilde. So your book writes LA of x for the image or this new space, um, the image of x tilde, let's say, or this space. And then also writes Lx for the image of x. The point is that the image of x tilde is in the image of x, or LAX is inside L of x. Um, I would like to say that LAX is inside LA, but unfortunately that isn't. But that's the way, if this was LA, that would work perfectly. So LAX is inside LX, or image of x tilde is inside image of x. Um, so why is that? Again, we discussed this last time. So if you do it, um, the columns of x tilde would be linear combination of the columns of original design. And so any linear combination of the columns of x tilde would be another linear combination of the columns of x. So anything in the image of x tilde would be in the image of x. So we have this nested subspace behavior, which we're going to use. So let's say this is the image of x tilde. Just you'll use the two notations because your book uses one, I use the other. And then the dimension of this new space, as we discussed, is p plus 1 minus q. Okay. And so what are these spaces? These are basically the models that we have for the mean vector. Okay, so if you recall, if I call the mean vector here mu, all this linear model is saying is that the mean of y, that mu belongs to the image of x. What we can say is that under the null, equivalently, we are imposing the condition that mu belongs to the image of x tilde. So if you go down here, I can write the same hypothesis in this format. So the model is like y is mu plus epsilon. Under the null, mu belongs to the image of x tilde, or LAX. Under the H1, mu belongs to the image of x minus image of x tilde. So this is like saying it's in the image of x, but not in the image of x tilde. It's the part of the image of x that's not included in the image of x tilde. Okay, so this is like a geometric way of expressing that hypothesis. In terms of in terms of beta, we are writing in terms of mu. Okay. Hopefully this is not too difficult to understand because we already are familiar with viewing regression as like, yes.
What's the backslash?
This is like a set notation. So if you have two sets, A bracket slash B is like A intersect B complement. Okay, it's the complement of the image of x tilde in the image of x. So whatever is not in the image of x tilde will restrict to image of x. We are still in the image of x, but not in the image of x tilde. Okay, so the full model assumes already that mu is in this image of x, then null asks whether mu lies in the smaller subspace, which is imposed by the constraints of beta. So far, so good. So that's going to be the way we do that geometric kind of interpretation and all the other interesting properties would follow from this picture. Questions? Okay, so in the example that we did earlier in the last lecture, as well as it's the same kind of situation above, that if you have beta 0 equal to 0 and then beta 1 equal to beta 2, the effect is that you get this new design. So you go from the image of this to the image of that. That we already saw this. So the idea is that now we're going to fit the two models, which is equivalent to projecting. So you project y onto the LA or the L of x, you get mu hat, and you project y onto the LA of x, you get mu hat a. And these operations can be done using the corresponding hat matrices. If you recall, every subspace has a hat matrix, so this projection is really h times y. And that projection is also like h a times y, where h a is the projection onto the image of x tilde. You can explicitly write it as x tilde times x tilde transpose x tilde inverse times x tilde transpose. But anyways, doesn't matter. Like the formula is just there is a unique projection operator. And so once I do that, I get these mu hat and mu hat a, and I can compare them somehow. And then we are going to use the assumption that we had, the E2 assumption, the normality. Okay. So far, so good. So let me argue or give you a picture when the noise is zero so that you can see that by comparing mu hat and mu hat a, you can figure out the relation. So if the noise is zero, y is just equal to mu. And then the test is going to ask us to fit the two models. So under the H1, I just know that mu is in Lx, but not in La of x. So if I plot Lx, let's say Lx here is going to be, let's say this plane. And then Lax would be some, this is the subspace under the null model for the mean of y, it would be some smaller subspace, let's say this line. And so because we are not assuming that there's like we're assuming that there's no noise, and mu is already in the Lx, you can see that so this vector is going to be y as well as mu. And then it would be Lx. And then if projected onto Lx, what would happen? The vector is in Lx when I project it.
Nothing up.
Nothing there, so it just remains there. So you get back itself. So this is the part that I'm kind of setting this equal to mu hat. So mu hat would be the same as this. So all of them are on top of each other. Y is equal to mu is equal to mu hat. Okay. However, under the alternative, this y is not in LAX. Okay, so it's in LX, but not in LAX. So when I try to project it onto LAX, I get a genuinely different projection. So I get mu hat A, and then you can see this is the difference. So the colored vector is mu hat minus mu hat A. So I get a non-zero difference between the residuals, sorry, between the fitted values. Okay, and then compare this with the case where we have, we're under the null. Here mu is going to be in the smaller subspace. And now I have y, which is equal to mu, lying on this. And so when I try to project it on either of the subspace, on the bigger subspace Lx or on the smaller LAX, I get back the same thing because I'm in the same subspace in each case. So both the projection onto the bigger subspace and the smaller subspace kind of match and match the original vector. So everything basically is equal, so there is no difference. So mu hat minus mu hat A is going to be zero. Okay, so this gives you the idea that there is this kind of simple geometric reason. So under H naught, when you do the projections, both are going to be the same. Nothing changes. But when you're under H1, one of them would be different than the other. So when you project onto the full like LAX, but the full model, you're not going to lose anything. But when you project on the reduced model, you lose a little bit of mu, which is not. So this part of mu, which is not in LAX, is reduced to zero. So you see a non-zero difference. And so by just looking at this difference in the noiseless case, you can tell which situation you are in. Does that make sense? Yes.
I don't know if this is a question. Geometrically, it makes sense to me, the intuition. But I guess when we project, my question is, when we are projecting a vector onto a subspace that is the element of a subspace that's already that the vector is already within it, that projection is valid.
It's not an element, so this is a subspace. So LAX is not an element, but it's like a subset, right? So it's a valid subspace. So you can project onto it, right? It's just that it's a subset of the bigger subspace. You can have two nested subspaces. So imagine you have a plane and then like the let's say XY plane, and both the x-axis and y-axis are subspaces, and they basically live in the same space. So I can project onto the x-axis, or I can project onto the plane, or I can project onto the y-axis. All of them are valid. Right, that's going to happen. Or like it's possible. No, no, that's happened. Just I could do is valid to do it. Okay. Any other questions? Okay. So what we want to do is we want to measure this difference, and kind of it measures like the part of mu that's like gets killed by the constraint. So I can build a test by just checking how large this is. If it's close to zero, I'm going to not reject. If it's large, I'm going to reject. The only issue is that how large should it be for me to reject? And then this is where the statistics comes in. I need kind of a measuring how large this gets, because this is not going to be zero when you have noise. Okay? Even if when you have, we'll see, even if when you're under the null, when you have noise, this is going to be, picks up some of the noise. And so the norm is not going to be perfectly zero. So we have to determine exactly where we want the threshold. So to see that, I mean, this is not going to be exactly zero. It's just really easy to do a little calculation. So under null, mu is in LA of x. And then we have this model for y. We're going to apply both of the projection operators or matrices. So for mu, I'm going to apply it to y. You get hy. And then just plug in mu, sorry, y is equal to mu plus epsilon. I get h mu plus h epsilon. And I'm claiming that h mu is equal to mu. Is that true? Or why is that true? Yes.
Mu is in image X and H is a projection matrix onto image X.
Yes. So here, let's say under null, we're in this LAX, which is inside L of X, which is really the image of X. So we are in the smaller subspace, which is inside the bigger one. So really, nothing changes. So when you project, h mu is mu, and then I get this expression, mu plus h epsilon. Now, if I project onto the LA of x, I apply the projection operator and get the same decomposition, HA mu plus HA epsilon. And then I'm claiming that HA mu is again mu, right? For the obvious reason, because mu is also in the smaller subspace. So projecting doesn't change. So I get this. And then when you subtract, so this is really the reason mu is in LA of x inside LX. And so when I subtract, you can see what happens. So when you subtract, the mu's cancel out and get h minus HA times s. Okay, and this is generally not going to be killed because the noise is really not in any particular subspace. And so the norm of this is going to be non-zero. And what I need to do is kind of figure out a way to measure the norm. Okay, and this is what we're going to do. We're going to try to find a distribution of the norm squared. And roughly what we're going to show is that this guy is a projection operator or projection matrix, and then I know how to deal with the norm of a projection matrix times a Gaussian vector that we have figured out before. Okay, and then, I mean, there's a bit of thing that we are going to also compare to this. This is going to be the residual of the full model, well, that we'll see. But I'm gonna try to figure out the distribution of this under the null so that I can set up the threshold. So far, so good. Okay. Let me maybe do the geometric picture first. So this geometric picture is going to help us a lot in general. So this is the general picture. When you have noise, so y is mu plus the epsilon, and epsilon is like pushing it outside the L of x. So although the mu is in there, I'm not showing the mu here. The y is not going to be there. So when you try to project, I can project it onto the Lx, the bigger subspace, I guess mu hat. So I get a genuinely different vector. And then if I project onto this line, I get the mu hat A. And this is also going to be different. And this is going to be true even if I'm under the null. Okay, even if the mu, because we saw like the difference is going to be, this side is not going to be necessarily zero in general. Let's see. And then I get this difference. This is the difference that I care about. And then because of the projection, the property of projection, that the residual is orthogonal to the space that you're trying to project, there's a lot of right angles in this picture that you can also kind of infer. And some of it we are going to use. So for example, we know that this E, right? This E is going to be orthogonal to anything in Lx. Okay. And in particular, it's going to be orthogonal to mu hat A, and the difference. But we also know more. There are a lot more. So for example, EA is going to be, this guy, E is going to be orthogonal to mu hat A and anything in LAX. Okay. And so this triangle is going to be an orthogonal, like a triangle with the right angle. And this triangle is also going to be like that. And it turns out that this triangle is also going to be like that. But we'll see, like the one that we, there are two of them that are important. This one is important for us. And so this angle is a right angle. We already know, right? Because E is orthogonal to everything. So it's particular orthogonal to mu hat minus mu hat A. So I get from this, I get a Pythagorean theorem. EA squared is equal to norm E squared plus mu hat minus mu hat A squared. And this is kind of showing that the residual of the, or the RSS, the residual sum of squares of the reduced model is going to be always at least as large as the full model, because this is non-negative, right? And so this extra piece there, which we're going to use to build our test statistic, is what you lose because of the constraints on beta. So the model cannot capture that part of the variation. And so the reduced model is going to show, like you see it in the residual. You get a worse fit. And how much worse? So instead of, for example, looking at this, I can look at the difference of the two. Because of this Pythagorean theorem, they're the same. Okay, so that's often easier. So you fit the models and you compute the RSS and then just compare the RSS. Yes. What am I talking about? Yes. So when I said the constraint caused this, what are the constraints here? There are different ways to state them, right? There are some constraints under the null, right? So you can think of it, the constraints being on beta, right? So these are the constraints on beta, right? So A beta is equal to 0. Do I have it here? Yeah, for example, these are the constraints. The constraints that we put on the coefficients, which then translate into constraints on the mu. So you can view it as constraints on the mu. So under the null, we have a smaller subspace for mu. So it's more constrained than if we were not under the null, right? So you can think of it as less degrees of freedom. You can see it here. anything in LA of x is not allowed to move like in this perpendicular direction. So if you look at the perpendicular direction, so this direction is orthogonal to that line, but it's still in LX. Okay, so this direction is lost. Like you remove this, then we don't allow the mean vector to vary in this direction. So it's constrained to only vary in this direction. That's another way of saying it. Okay. And that's a good place to tell you this direction would be like has a kind of a we can write it like this. So this space is Lx minus in this fancy notation, like circle inside minus LA of x. So it's somehow we remove the directions of LA of x from L of x, and then we get this. The formal definition is that this is really Lx intersect the orthogonal complement of LA of x. Okay, the LA of x is a subspace. It has an orthogonal complement. The orthogonal complement is anything that's orthogonal to LA of x. And we take the intersection with L of x. Among all those directions that are orthogonal to LA of x, only those directions that are inside L of x, those are the ones that I care, and those are exactly this. So the full orthogonal complement to that reduced subspace would be a plane. Because this is a line, there's a full set of like two directions that I can vary, but like when you intersect L of x, in this case, it would be a line. Okay, so that particular subspace is very interesting because it tells you the directions that are orthogonal to A of x, but still remain in L of x. Okay. Intuitively, it's just you remove those components from the vector. Like if you have a vector in L of x, you remove the components that are in this direction, you're left with only the components that are in that direction. So this is kind of a relative orthogonal complement. Okay, and it turns out we'll see that this guy actually lives in this space. Okay, this guy lives in that space, and for that reason, this would form a right triangle, like a triangle with a right angle. Okay, we'll see this. Okay, but this subspace is interesting. So, and this is exactly the subspace that I kind of don't allow on there. So this is my constraint. Like this is saying you're not allowed. It's like a forbidden subspace. Okay, so we get this Pythagorean theorem, the reduced model RSS, or we write it as SSE, I believe, in this course in the book. Sum of squares of error, also SSE in the book, is equal to the full model RSS plus the extra cost of the constraint you want. Like this is what the constraints are causing us in terms of the fit of the model. And that this part. Also referred to as an additional sum of squares. You'll see later. So let's prove. I want to prove an interesting result that this guy h minus ha is a projection. Okay. Then I can use that lemma that I had from lecture 7 that tells me what the distribution of the squared norm of a projection times the Gaussian vector is. Okay, so this notation I already introduced. So if you have two subspaces, like W is inside V, then we write V minus W to denote V intersect W perp. Okay, this is called the orthogonal complement of W within V. And it's not hard to argue for yourself that the dimension kind of behaves how you expect. So the dimension of V minus W would be dimension of V minus dimension of W. This is like the way that we subtract two subspaces. We also had an addition, if you remember. But I'll let you remember. We'll go back and recall what that was. Anyway, so this is the notation. So let H be the projection onto L of X, or the image of X. Let HA be the projection onto LA of X, or that image of X tilde, if you want. And we know that like let's say this is part of the assumption. So A of x is inside L of x, which is the case for us. So we have two projection operators that are projecting onto two subspaces, one of which is inside the other. Then if I look at the H minus HA, the claim is that this is going to be an orthogonal projection matrix, and it's going to be projecting onto this difference of the two subspaces, and its rank is going to be Q, assuming with the uh, basically the this is going to be the difference. So there, I'm not specifying what Q here is, but it's just the same thing that we had. So it's really the dimension of the subspace. We'll see. Okay, so this result is not going to be true if this relation is not true, or like you don't have that relation. So if you just subtract two projection operators in general, you don't get a projection operator. But if one of the subspaces is nested inside the other, then you have this very nice result that the difference would be still a projection operator, and it projects into that relative orthogonal complement. Okay, it projects onto the orthogonal complement of the smaller one relative to the bigger one. Is this statement kind of clear? Okay, so let's see how would you guys prove this if you wanted to prove this. If I give you as a like an exercise or work problems or like exam problem, can you try to prove it? Yes.
Matrix maps something into the kernel of the subspace defined by the L of x minus LA.
Can you say the first half? We want to show.
The H minus HA projects into the kernel of that subspace.
Oh, I don't want to say that it projects onto the kernel. I just want to say that it projects onto the subspace itself, not the kernel. Yeah. So this projects onto, this is going to be the projection onto Lx. Yeah, I mean, and the kernel would make sense for a matrix, not for a subspace. So this will have a kernel, and you can try to figure out what the kernel of it is. But what we were saying is like the image of it is that subspace, and it's actually projecting onto that subspace. Okay. We are not worrying too much about the kernel, although the kernel of it is also interesting. Now, how do we prove it? What do we know about projection matrices? Can you say that? Yeah. Yes. So we know that orthogonal projection matrices are like idempotent and symmetric, and this is like a characterizing property, or these two together characterize. Any matrix that has these two properties is a orthogonal projection matrix, and vice versa. Okay, it's an if and only if. So at least the first half I can prove by arguing that by just doing algebra. So you square it, for example, this matrix and show that it's idempotent, and also argue that it's symmetric. And so let's do that. And for this, we need these two identities, which are kind of not difficult to show. So H times HA is equal to HA, and HA times H is equal to HA. Okay. The first one, this one, if I want to show, I'm going to apply both sides to a vector, and if I can show that these two vectors are the same for any y, then I have the result. Look at this, like let's call this z, for example. So when I apply HA to y, I'm projecting y onto LA of x. And so this z is in LA of x, but LA of x is also inside L of x. So when I apply h again to z, it's going to leave it invariant. Okay, so this identity is really saying when you project onto LA of x and you project whatever you get onto the bigger subspace, nothing changes. Okay, so that's that, which is geometrically very straightforward. The second one requires this fact from linear algebra that if you again write it in this fashion. So because this, like, first let's go back to, because this holds for any y, then the identity holds for matrices. Okay. You want to prove a result for like matrices are identical, you show that they act when they act on a vector, they produce the same result for all possible vectors. The same goes here. If I want to do this identity, I would try to prove that HA times H times Y is equal to HA times Y for any Y. And this geometrically is saying if I first project onto the smaller subspace, sorry, if I project onto if I want to project onto the smaller subspace, it's equivalent to first projecting onto the bigger one and then projecting onto the smaller one. So geometrically, this is saying to get this guy, I can first project onto the L of x and then project this mu hat onto this line. I would get the same thing. So rather than directly projecting y, I first project onto the bigger one, I get mu hat, and then I project mu hat onto that line. So this one intuitively is clear, and I'm not going to prove it, but you're welcome to prove this, okay? So this is in a general fact. If W is inside V, applying the projection onto the bigger one, sorry, the smaller one to the projection to the bigger one gives me the projection onto the smaller one. Okay, so it's like a two-step projection. You first project onto the larger one, and then whatever is left, you project onto the smaller one. And the way to prove this is via the orthogonality principle. So you have a candidate for the projection, which is this second stage projection, and you show that the residual is going to be orthogonal to the smaller one, and then they're done. Okay, so prove this as an exercise. Prove as an exercise via orthogonality principle. Okay, so equipped with these two facts, I can go ahead and verify idempotent. So P is equal to H minus H. This is I let P equal to H, P equal to H minus HA. P squared would be H minus HA times H minus HA. And then you just multiply things out. The first term would be H squared, which is equal to H, because H is idempotent. And then I get the cross terms, H times negative, like minus H times HA, and then minus HA times H. These are the cross terms, and I get HA squared, which happens to be also equal to HA, because HA is also idempotent. And then the two middle ones are also HA by these two identities, sorry. So this is going to be also HA, and this is going to be also HA. So what happens is that I have H minus HA plus HA. Things cancel out, I get H minus HA, which gives me P. For the transpose just acts like on these separate, you get the H transpose minus HA transpose, and so you get P back. Okay, so this proves that this is a projection matrix, right? And then orthogonal projection matrix. Does that sound good? And then what this means is that it's projecting onto its image. And I just want to maybe argue that now projecting onto that difference. And this is also not really difficult. So I can write H as HA plus P. This is from the definition of P. Okay. And then I notice that HAP is equal to P times HA is equal to 0. Okay, these two matrices are kind of, you can say not orthogonal, but when you multiply it, you get 0. And so what this is saying is I can write any vector in this format. Hy is HAY plus H minus HA, that's the P times Y, right? So I have a decomposition of every vector into these two pieces, and because of the fact that these two matrices, when you multiply, you get 0, these two pieces are orthogonal. Okay. If you look at the first component transpose times the second, you can easily see that this matrix identity will tell you that's zero. So I've managed to express anything. So this would be a general vector in the image of H, which is Lx. And this is going to be a component in the image. So this belongs to the image of H, which is really Lx. And this belongs to the image of HA. This is going to be in LA of X. And this is going to be orthogonal to LA of X, right? And you can also see that it's going to be also already in here, because it's really not difficult to see that H minus HA, whatever, like the image of H minus HA is already in there. So this is going to be in LX, but not here, because it's like, sorry, it's going to be orthogonal to this by this property. So this has to belong to LX, not LAX, like, no, not like subtract LAX, okay? Because this is orthogonal. You know that this piece is orthogonal to this, or basically from this, it would be any vector which is in the image of HA. And so this piece is orthogonal to the first piece, and already in there. This one is not easy, it's just because both HY and HA are like both HY, like HY is in the image of X or LX, and HAY is also in LX. So the difference is also in LX. So they are in LX, but orthogonal to the first component, which is any vector in LX. So this is the orthogonal decomposition of the LX basically into two pieces, this and this. It's very much like the orthogonal decomposition that we had for the full space. If you remember, any orthogonal complement pair, like V and V perp, like split the space into two pieces. This is similar, but we're doing it relative to the LX. So as if this LX is just the ambient space. And so because of this fact, at least this would imply that this is equal, like this is a subset, the image of P is a subset of this, but you can also argue that it's exactly equal to that by kind of maybe doing a dimension count. So the dimension of the image of P is the rank of P, which is equal to the trace of P because it's a projection operator, if you remember. The eigenvalues are 0 and 1, so for projection operators, it's equal to the rank of P. And rank of P is rank of H, or trace of basically. This is trace of H. This is the trace of HA. So trace of P, trace is linear, the trace of H is P plus 1. And the trace of HA is P plus 1 minus Q, because that's the dimension of LA of X we determined. So the difference is Q. And this matches the dimension of this subspace. The dimension of this is like exactly the dimension of L of X minus dimension of LA of X. I think that's the first, this one is enough to actually show what we want, but this is an extra confirmation that the dimension, the rank of P matches the dimension of that space. So they have to be equal. So the image of P has to be equal to this because it's inside it, and the dimensions are the same. But even if you don't do the rank calculation, the fact that we do this split is kind of going to be enough. Is it going to be enough? What's the 10th? Anyways, so just verify for yourself these two. From these two, you can argue. Yes.
I missed this, but why is HAP and PHA equal to 0?
Why is that? Anyone can tell me. Why HAP and PHA is 0? So HAP is equal to HA times H minus HA. This is HAH minus HA. So this is 0 because this. Okay, it's these two identities. Just rearrange. Okay. It's slightly like tricky, but it's the same kind of argument. If you want to be really careful, you can argue carefully that first show that the image of P is inside this, and then argue by, for example, dimension, because the dimension of the two spaces are the same. If you have two subspaces that are nested and the dimensions match, they have to be equal, because there's no other room for the other guy to, like, it's like a fact of linear algebra. Um, or you could argue it differently. But anyway, so the kind of like the idea is that this shows the two pieces when you do the decomposition are orthogonal, and this is kind of the key idea, and everything kind of basically follows from these two geometric facts that you can kind of iterate these projections. Okay, spend too much time on it, but at the end of the day, you prove that H minus HA is a projection matrix. I mean, this the first part is easy. The second part, that it matches this, and this happens to have dimension rank Q, because that's basically the difference between the dimension of the two subspaces. Okay, that exactly is equal to the number of constraints or number of degrees of freedom that you lose. Okay, I think we spent so much time on this. Now let's see how we can use this. Any question about that? This is how we can use it. So we saw that mu hat minus mu hat A is equal to H minus HA times epsilon. And I've now shown that this is a projection matrix of rank Q. We recall our result from lecture 7, that if you have a projection matrix, orthogonal projection matrix of rank R, and you have a, let's say, vector epsilon, normal with mean 0, covariance sigma squared in, then P epsilon squared divided by sigma squared would be chi squared with R degrees of freedom. Okay. And so we're going to apply it to P being H minus HA, the R, the rank would be Q. So just plug in here, and you get that the norm of mu minus mu A squared divided by sigma squared is, sorry, where is my highlighter? Okay. This norm squared divided by sigma squared is chi squared Q. And the key is this is under H naught. Okay, not necessarily under H1. And why is that? Because this identity only holds under H1. If you go back to a couple of slides earlier, the reason why this holds is because the mu is, when you apply the H and HA, both leave mu invariant, and so they cancel out, and that's only happening if mu is in both subspaces. So this is under H naught. If you're under the alternative, there's some extra term here, which is the kind of residual of mu that the smaller subspace can't explain. But under the null, this is going to be chi squared Q. Okay. If I want to use this result as a calibration to set the thresholds for the test statistic, I have the issue with the sigma squared, which I don't know. And our solution here would be, what would be our solution? In statistics, if you don't know something, what would you do? Most often you estimate it and just plug in. That's the easiest thing to do. So we have an estimate I can plug in S squared, but then that would destroy this distributional identity, because that would be a random quantity. But we can, again, you're lucky in the sense that that the squared is going to be independent of this quantity. So if you want to be a little more precise, from lecture 7, we saw that this is the residual for the full model, right? Norm of E squared divided by sigma squared is also chi squared n minus P minus 1. And the reason why that was is exactly because you can write that residual out of a projection matrix I minus h times epsilon. Uh, uh, and so this is like E is I minus h. Epsilon, I'm just applying that result to this vector. And so that was exactly how we proved this. And this is um, generally under the linear model, so there's no h naught assumption needed here. And so I have these two statements, and somehow if I divide these, you can see the sigma squared go away. And what I need is for them to be independent. Or at least I need to know the joint distribution and know that kind of when I do this operation, what happens to the ratio. As it turns out, we are lucky, so these are going to be independent. So what I need to show is that these two quantities, mu hat minus mu hat A squared, whether divided by sigma squared or not, it doesn't matter because the randomness is in the numerator, and E norm of E squared, whether divided by sigma squared or not, these are independent. If I can show that, then I am in business. Okay, I can build like a test statistic. Right? So the marginal distributions are not going to be enough. Okay, so you can have two things that are marginally distributed, even if they kind of I mean, it's very tempting to try to divide them, but it could be that they're highly correlated or highly dependent. And when you divide, the distribution could even like depend on the unknown parameters. This fact has to be, I mean, you have to think about it. It's not so obvious. But once you're independent, then the joint distribution is fully specified by the marginals, and you know that the joint distribution is not going to depend on any unknown parameters because the marginals are not. And so when you divide, you're sure that the whatever the distribution of the result is, even if you don't know, it's not going to depend on the unknown parameters. You can do it by simulation if you want, or anything. In this case, again, you're in luck, and we know like it's a known distribution. So what we're going to do is try to claim and then prove that under E2, these two quantities are independent. We need a normality assumption for independence, so we need the full distributional power of that assumption. So how do I show this? How do I show that they're independent? So you can look at the form of these, any like first steps, like suggestions for. Yes.
The first step would be show that mu hat minus mu hat A and y minus mu hat are multivariate normal.
Good, great. Yeah, the first step is exactly that. So I'm going to show or argue that if I, let's say, stack them together as a vector, they have a multivariate normal distribution. So why is that? How can we argue that?
Because they're both linear transformation of epsilon.
Yes, exactly. So this is like a linear transformation. H minus HA times epsilon. And this is I minus H epsilon. So if you want to be really formal, I can pull this out. I get a single linear transformation here times epsilon. So this is some A times epsilon. It's a linear transformation of epsilon, certainly an affine transformation. So by the affine transformation property of multivariate normal distribution, I get that this is multivariate normal. So that's good. So we know a lot about multivariate normal distribution, like random variables or random vectors. So what is the next step? Step one. This is true. Step two. Yes.
Show they are correlated.
Show that they're uncorrelated. And then we get independence for free because we are under the MVN distribution. So how do I show that they're uncorrelated? Yes, so I'm going to compute the so-called cross-covariance matrix. So these are two vectors. So this is an instance of these matrix valued, let's say, covariance operator. So or rather like it takes two arguments rather than a single argument. Can't say it by Mary yet, but you've seen this in your midterm and in your homework, okay? So it's like it's an extension. So these two vectors are, when they're the same, you get the covariance matrix, but I can apply to these. I'm going to plug in. I get h minus HA times epsilon and I minus h times epsilon. So what's next? It's like a famous formula here. You'll play. You know,
If without the H minus H is to the right and if I minus H transposes to the to the right hand does that.
yes, so on the left, I'm going to pull out, each one comes out on the corresponding side. So this comes out to the left, the other one comes out to the right and gets transposed. You remember how these things are defined, and this is sigma squared I. And then this simplifies a little bit, right? I minus H transpose is just I minus H because it's a projection matrix. And so once you multiply things out, I can put sigma squared here. I get I H minus HA times I minus H. Let me expand. I get H minus H squared minus HA plus HAH. Okay. Does this simplify? Yes.
H squared is H and
Right.
H is H.
Yeah, this is the first two would basically sum or like add up to zero because of idempotence of H. And this second piece is really HAH minus HA, which is also zero. That's another one of these identities that we showed earlier. So the whole thing is zero. So uncorrelated, correlated plus MVN. So we get independence. Okay. So we showed that basically mu hat minus mu hat A. Sorry, we showed that this vector mu hat minus mu hat A is independent of E. So can I conclude now that what I want, the norm, let's say, this guy divided by sigma squared is independent of norm E squared divided by sigma squared. Can I do that? Am I about to conclude that? Why?
Because even if the sigma squared is there, the independence still holds.
Yeah, okay, so sigma squared is constant, so you don't need to worry about it. But I'm squaring, like taking norm squared. This is like a nonlinear operation. What can I still claim?
Functions of independent.
Yes, so basically any reasonable function, any function that you encounter in your life, any measurable function of these two, once you establish that two random variables or two random vectors are independent, any function of one is independent of any function of the other, no matter how complicated, as long as they're measurable. But you don't see non-measurable functions in the wild unless you try really hard to make them. But any function like this is like norm squared is perfectly benign function. So we get that. Okay. That's the kind of strength of independence. Uncorrelatedness does not have this feature. I keep repeating this because it's interesting. But independence is strong enough that once you establish two things are independent, any function of one piece is independent of the other piece, any function of the other piece. Okay, so we got our result. So this is just repeating that. Okay, so now I can use this fact about the F distributions or an F distribution. So if you have a random variable which is chi-squared with a degrees of freedom and another random variable which is chi-squared, has a chi-squared b, so chi-squared with b degrees of freedom, and they're independent. And then if I form the ratio properly normalized, just normalize each one by its degrees of freedom, and then take the ratio, then the result will have an F distribution with degrees of freedom A and B. Okay, this is kind of a definition of the F distribution. Applied to our basically the two quantities of interest for us, we get that so mu hat minus mu hat A squared divided by sigma squared, that's chi squared with q degrees of freedom, and is independent of like e squared divided by sigma squared. And if I divide that by its degrees of freedom, which is n minus p plus 1, that this ratio would have an F distribution. And this ratio, you can see like the sigmas would cancel out. And then I'll leave the degrees of freedom there. And so this statistic is gonna, this is really E squared. It's easier to write it as norm, but you can also write it this way. It's more verb. Yeah, I mean, it doesn't matter which way you write it. Same as E. So this is under H naught, we have an F distribution. Because I have an F distribution under H naught, I can just set a threshold. So this is a non-negative quantity I'm gonna want to reject. So roughly it's normalizing this basically loss that we had in fit by the size of the RSS of the full model. So it's normalizing it so that basically it doesn't depend on the problem. It's problem independent. And so under the null, I'm going to reject if f is bigger than a gamma, level gamma, and I set it equal to 1 minus alpha. This you can set based on the quantiles of f distribution, and you get your test. So, I mean, we'll do that maybe. But it's just standard at this point. So you look at the quantiles of the F distribution with the certain degrees of freedom. So Q here is the number of constraints, and the sample size, P the total number of variables. And here the one is saying that you have an intercept in the model. If you don't, you can drop that, or you should drop that. And so you get this. This is like if it's G gamma. And then if I apply to the F, this would be my p-value. And I can report by saying, I mean, this is equivalent. The test would be p hat less than or equal to alpha. Yeah, either set it equal to 1 minus alpha or report the p-value. So either this or equivalently like reject if f is bigger than G inverse of 1 minus alpha. The two tests are equivalent. Sounds good. Okay. We did it a little faster than the morning session, so that's the test. So reject H at the level alpha when, so this gamma would be basically, this would be, you can say FQ n minus P minus 1, 1 minus alpha. That's like the, is that, I'm not sure if I used the notation right. So what we want to do is, yeah, sorry, this would be, yeah, this would be alpha here, I think. Not 1 minus alpha. This should be alpha. So what we do is we set it equal to alpha because that's the probability of rejection, and then it would be the 1 minus alpha quantile. So this is the quantiles, and unfortunately that's I would say like they'll write that as f hat if you want. This is a random variable. This is really just a quantile function to not be confused. Like to not confuse the two. Yeah. Yeah, so that's the correction here. If you define it like this, we want to set this equal to alpha. So it would be G minus 1 of alpha. This is like the complement of this quantile function like this. We take the complement CDF and invert it, which would give you this equivalent to just looking at the inverse CDF, that's the quanta, but divided movement stuff. Okay, so that's our test. So far, so good. So we built a test. This is fairly general because we didn't make any assumption about the particular nature of the constraints that we put on the node, except that they're linear. And we have independent, like linearly independent, like Q linearly independent linear constraint. And there are a lot of examples of it that we'll use later and then discuss the statistical one. Okay. Let's see what this is saying. Why one-sided rejection? Yeah, so this is why we do one-sided. It's good to think about because you could imagine that maybe under null, this is f, but the alternative it would be smaller rather than larger, but it's going to be always larger. So under the null, this is going to be on average always larger. And I'll let you guys think about it, okay? Maybe might be obvious, but it's a good point. Yeah, we do a one-sided test here. And the p-value would be basically that. Okay, I think I have couple more. We're almost done, but what we're going to do is, this is just an alternative way of writing things. So if you just followed what we did, this is really that Pythagorean identity. So this is like EA, and this is E. And so this is just saying norm EA is squared is equal to norm E squared plus this quantity. So because I can write this, the so-called, this is called additional sum of squares. I can write it as SSE of this is the SSE of the reduced model. Let's call it SSE of A, let's say. And then minus the SSE of the full model, which is just the SSE divided by Q. And the denominator, if you remember, is just the norm of E squared. So this is the SSE of the full model. So this is a very compact way of writing the same statistic in terms of the residual sum of squares. Okay, so you fit one model, a large model, you get like a number here, and then you fit this smaller, like a smaller model, and this would be, by definition, the SSE would be larger. So you look at the difference, you divide by Q, and then divide by the SSE of the full model, divide by n minus p minus 1. And this way, if you have actually a bunch of nested models, just having the SSEs, you can compare them. This is a very nice way. Maybe we'll talk about that a little bit later. Like you can have like a sequence of nested models, and any two you can compare by just comparing the SSEs. You get an F test. Yeah, so another way of seeing it is that if this is large, this can be large if this guy relative to this is large. So it means that the fit of the reduced model is bad. This is small if they're kind of the same. So you fit the larger model, you fit the smaller model, that the SSE doesn't change much. You're probably under null. It's just good to not, let's say, reject null, but if the difference is too wide and then the gap is too large, and how large is relative to the actual SSE, it's like a relative gap. This like properly normalizes. So like a beautiful statistical normalization. So if you just normalize it properly, if you ask me how large should I interpret as large, exactly as large as this can predicts. Okay, I think one more example. Yeah, this is just doing it. Let me just do this and then we're done. I mean, if you want to do this if I don't have I think, numerical example here, but we can do a numerical example later. So in that model, for example, if you want to do that hypothesis test, you fit the two models, and you can do it in R, for example. You compute the SSEs, Q is 2, n minus p minus, like p plus 1 would be 4, so you just form this, and then you just reject at this level, and this can be done. I mean, if you're in R, this whole thing can be done by this. You fit a linear model using the LM command. That would be the reduced fit. This would use an LLM command, and this is an LLM like LM command. This would be Y and X. This would be X tilde. This would be Y and X. And then you do this ANOVA command between the two fits, and it just does this for you. But you can also do it by hand and just verify. Sounds good. I think we're done. Next time we're going to come back and talk about like special cases and